Hello, everyone. Welcome back once again to the 2020 Small Farms Winter Webinar Series hosted by University of Illinois Extension's Local Food Systems and Small Farms team. Once again, this is Zach Grant, Local Food Systems Small Farm Educator in Cook County, moderator and coordinator for your weekly dive into all things small farms. We really appreciate you joining us for these webinars once again, and we'll do our best to begin and end within the space of your lunch hour. This is a very tight time frame for our educator to deliver this presentation, so we want you to limit your questions to the Q&A box during the presentation. I will do my best to make sure our presenter answers them as time allows, or the moderators may be able to answer as well. This presentation is being recorded, and I will email you a link to the archive presentation as soon as possible after this concludes. There will also be a link for a very short online evaluation for this presentation included in that email. We very much appreciate your feedback as always. I will also be sharing a screenshot, or rather Bronwyn will be sharing a screenshot of the QR code in the last slide of today's presentation. You can immediately go to the evaluation if you scan that QR code with your smartphone or QR code reader app. We are using Zoom's webinar platform this year, so there's just a few additional features I want to point out. First of all, there is a poll that is now actively open that some of you are responding to. This is voluntary and anonymous demographic information that's very helpful for us in Extension. There's also the Q&A section and chat box section. The Q&A section, we would like for you to list your questions for the presenter, and the chat box is more generally used for other technical questions related to the webinar. So this week's webinar is presented by Bronwyn Aly. She's a colleague of mine, local food small farm educator housed in Gallatin, Hamilton, Hardin, Pope, Saline, and White counties in far southern Illinois. She's an extension educator that works primarily around local food systems and resource management for small acreage systems. She works with local producers interested in specialty crops, including small fruit, vegetable, and tree fruit. Bronwyn is also responsible for managing the High Tillman program and specialty crops program and demonstration at the Dixon Spring Ag Center in Southern Illinois. Today, she's going to be leading us in a presentation about getting started in drip irrigation. So I'll go ahead and let her take it away.
All right, thank you, Zach. I want to welcome everybody taking your time on your lunch break to join me as we talk about some basic information to get you started in drip irrigation. When we think about drip irrigation, we probably need to define it. So looked up several different definitions from different sources, but this is a lengthy definition from the Food and Agricultural Organization of the United Nations, but I think it encompasses a lot of the factors involved in drip irrigation. We refer to drip irrigation sometimes as trickle irrigation, and this is where we are using a very low flow rate of water dripped on to the ground using a system of plastic pipes and tubing with outlets that we call emitters or drippers. And this applies water right at the, very close to the base of the plant. So water is delivered right into the root zone. And that is the only area in the field that is watered in this system, which is different than either surface or overhead sprinkler irrigation. With drip irrigation, applications are going to be more frequent as opposed to overhead irrigation. And this provides a more favorable high moisture level in the soil so that our plants can flourish and feel less stress. So for today, topics I want to cover in this presentation, talk about advantages and disadvantages of drip irrigation, discuss a little bit on design factors, things you might, aspects of your production and your farm that we need to consider when we're thinking about the components and the various parts and pieces that we need for installing a drip irrigation system. We'll talk about obviously components involved in that, some water sources, management practices, a couple of management tools, and some resources. And if we look at this page, when we the picture on this slide, when we think about one of the advantages that stands out to me is very obvious, is the labor efficiency that our operation can be afforded when we can use drip irrigation. If you look at this photo of tomatoes planted conventionally out in the field, there's no plasticulture involved. just drip irrigation. And if you'll notice, we could continue to do various field chores while we were irrigating our plants. If we needed to be tying, staking the tomatoes, if we needed to be hoeing around our plants, we could continue to do that while our irrigation was running. And if we were not using drip irrigation, but we were using an overhead irrigation system, all of the soil in this field would be wet and become muddy, and we wouldn't be able to as easily walk through the field or drive equipment through the field. So that's one of the advantages from a labor standpoint of utilizing drip irrigation. And some other advantages that we can see compared to overhead irrigation or other types of irrigation, drip irrigation is a lot more efficient in its water use. Approximately 90 to 95% of the water applied through the drip irrigation system can be utilized by the plant. If you think about overhead irrigation that is spread out across the whole field, there may only be 50 to 75% of that water utilized by the plant. So it's a lot more efficient use of the water that's applied to the field. It operates at lower pressures. You know, this is a low rate, low pressure system, and so we don't have to utilize as much pumping power, which can in turn generate an energy cost savings through the life of the irrigation system. Another great thing about drip irrigation is it's adaptable for all soil types, and we'll discuss some of that a little bit further, but whether you're on a sandy soil or a clay soil, we can adapt the components in the system to utilize on any of those soil types. We see improved yields and fruit quality. We're basically creating a lot less plant stress because we're able to provide a more constant, equal soil moisture environment to the plants so they can easily take the water up, have water uptake and not be stressed in a drought type situation. And because the drip irrigation is putting water on the top of the soil right at the base of the plant, we see less disease pressure because our foliage is not being wetted from irrigation as in overhead irrigation. We also see less weed pressure between the planting rows. Again, we're not wetting that area of the field, and so as it dries down, we don't have the moisture for the weed seeds to germinate, which again is another benefit. It's also really easy to fertigate, and fertigation is the delivery of fertilizer through the irrigation system itself. And a lot of times we may put fertilizer down in a pre-plant application, but through the course of the season we may need to add additional fertilizer, and being able to deliver it through our drip irrigation system is very easily done and pretty common practice for most growers. Drip irrigation is also easily automated. We can, if we choose to do so, we can add controllers or timers into the system, and we have control over not only the timing but also the amount of water that we can apply in a given area. And because the system is basically put together with various components of plastic tubing, repairs can be made very easily. And so these are just some of the advantages of drip irrigation. When we think about the disadvantages, one of the big things that come to mind are the emitters, the tiny little orifices in the drip tape that the water percolates or drips out of can become clogged very easily. And we'll talk about this more later in the presentation, and some things we can do to help mitigate that situation. Another disadvantage can obviously be the cost. We can have some high input costs initially. This could be anywhere from $500 to $3,500 or up, depending on the water source you're using, the size of the area you're irrigating, and depending on the water source, the type of components that you may need to have in your system to make everything function. If you're just starting out, maybe you're starting out and you have one high tunnel, and you have a municipal water source and water hydrant right by your tunnel. I would say a $500 initial input cost would get you all the parts and pieces that you would need to set up a drip irrigation system. While the high input cost is a disadvantage, we can think about it as an investment, because most of these parts and pieces we're going to be able to reuse year after year. So we may have an initial investment that can be pretty pricey up front, but we can continue to utilize those components for several years before they will need to be replaced. Something else to think about is, while most of the components in a drip irrigation system are reusable year after year, the actual drip tape itself is typically not reused after the season. We usually remove that from the field and need to dispose of it. And so depending on the size of your operation, drip tape disposal could be an issue, and it's something that you need to think about prior to purchasing 10 or 12 acres worth of drip tape. Know where you're going to go with that at the end of the year. While we don't have weed control, as much weed control issues between the rows and the planting, what we do see is that we will have to maintain some type of weed control within the planting row itself, because we are delivering water to the plants we planted there, but also any weed seeds that are in that planting row are going to be wetted up as well, and we will need to be able to control weeds around the plants themselves. And also, this is a more intensive management system. Unlike an overhead irrigation system where we kick the water on and maybe once a week and we run it for an hour or two, with this system we're going to need to be turning the water on multiple times a week, maybe daily, and in some situations maybe multiple times a day. And so it is a lot more intensive on the management side for that reason. Okay, so design factors. First thing we need to think about is, what's the soil type? Are we on a sandy soil, a clay soil, a loam soil? Are we, if we're just getting started, are we going to be irrigating in permanent raised beds that we've built in a high tunnel? Are we, if we're working in, maybe we're in an urban farming situation where we have created raised beds, permanent beds on a city lot, we can still utilize drip irrigation, but we need to think about what growing media we are utilizing. And so if you look at the picture on this page, soil type really affects how the water flows from after we are delivering it through the drip irrigation system, how it flows into the soil. So if we look at a clay soil, clay holds more water. It's a very fine textured soil, and so water moves very slowly down through the soil profile, and it will tend to want to spread out. It's also, once it gets a lot of moisture in it, it's slow to release that water out. And so we think about clay soils can stay saturated or beyond field capacity longer than, say, a loam or a sandy soil. And then conversely, if we look at a sandy soil, the pattern of water moving through a sandy soil doesn't really spread out much from the T-tape or the emitter itself, but moves really quickly down the profile of the soil. Sandy soil has got a more coarse texture, and it has a lot more air pockets, and it's more porous, so water is able to leach through or run through the sand as opposed to spreading out. This does allow for quicker water flow. It also has the potential to leach nutrients away from the root zone more quickly. The ideal soil type obviously would be if we look at the loam in the middle. So the water is able to spread out some, but also move down through the soil profile. Loamy soil is the best of both worlds. It is more porous than a clay, but it does have enough organic matter that it helps retain moisture and would be the optimum soil type. So if we were choosing a drip tape to put in our field, we would need to look at our soil type. And if we were on a clay soil, we would want to choose a drip tape where emitters were spaced further apart, 12 inches apart as an example. And we would use a tape that tells us that it has a low flow rate, because we want that water to come out slowly as opposed to really fast, because the water is not going to run through the soil very quickly. And if we have water flowing out at a higher rate, we can tend to saturate or flood our area. As opposed to a sandy soil, our emitter spacing would be closer together, maybe at an 8-inch or 6-inch spacing. And we would want that to be at a higher flow rate, but we may need to utilize a much shorter watering time period, but maybe have more frequent times during the day that we water. So the other thing to think about in design factors would be our crop that we're irrigating for and the area that we're going to be irrigating. Are we on a sloped ground? Are we irrigating a half acre? Are we irrigating in a high tunnel? Are we irrigating 10 acres? So we need to think about the size of the area, the type of area that we're irrigating in, and also the crops that we're growing in those. We need to think about our available water sources. Our initial costs up front with municipal water to get the system started might not be as high, but we will be paying a water bill each month, and depending on our water use, that could be pretty high. But if we have access to some type of surface water or a well on your farm, then you could utilize a different water source. Again, a higher upfront cost, but there's no water bill payment if you're running off of a pond or a well. And then also, do you have plans for future expansion? We wouldn't want to buy components for a system for maybe a high tunnel or a half acre when we ultimately plan to plant out 3 or 4 acres. We want to make sure that we have buy components in our system that have the capacity to handle future expansion. So what are some of the components? Depending on the water source and the system that you're setting up, we can have some or all of these components involved in our system. So if we're looking at our water source, if we're using municipal water or a shared water source, a backflow preventer is going to need to be in place. If we're using a surface water or a well water source, we were going to need a pump. All of the systems are going to need a filter, whether it's a screen filter or sand media filter. Pressure regulators are going to need to be in place. Our drip tape, the typical range of pressure that drip tape can handle is anywhere between 8 and 15 psi. And a lot of times the pressure running through our lines can be a lot greater than that, and we don't want to blow our lines out. So we need to make sure we've got pressure regulators in place to keep our system in a usable range for our T-tape. We have a control system in there. We're going to need some valves. If we're going to be zoning our area, we need to be able to shut sections of our system on and off. We also have the main line. So that's the line that's carrying the water from the water source to our drip tape. And we have different options for that. And then the laterals would be the drip tape itself. And then all the different connectors that we can utilize to put this system together. So here's basic components to connect to a hydrant from a municipal water source. So if you're looking at raised beds, maybe a small community garden, you're just getting started, maybe in an urban setting where we've got permanent raised beds. At our high tunnels at Dixon Springs, we use municipal water, and this would be a typical setup that we would use in our high tunnel. And you can see at the top we have a backflow preventer because we are hooking into a municipal water system. We need to make sure that we're not going to have any particles or fertilizer going back into a shared water source system. We also have in line a filter, and this is a screen filter using municipal water. We shouldn't have large particles in it. If there's a line break somewhere, there could be some dirt or debris that comes in, and this screen can capture that. Next in line we have a pressure regulator. I know the meter at Dixon Springs is running about between 40 and 50 psi, and so we have a pressure regulator in line so that we can drop that pressure down to about 10 or 12 psi, so we can not blow our drip lines up. And then we need to be able to connect from the pressure regulator into our main line, and so we'll have some type of hose-in connection to connect that, so the what we call the header components into the main line. This picture I put in, there's a lot of text on here, but basically if we were designing a bigger system where we were using a surface water source or a well source for our water, you can see we have a pump on the left. And as we move through the system, looking at the schematic from left to right, we would have a pressure release valve. Depending on how much pressure that pump is generating, we may need to put a relief valve in there so that we aren't blowing the rest of our lines up. We have a backflow preventer in. Next, we have a chemigation, or that could also be a fertigation injection area. And that could, in this schematic, it has it before the filter system. This could also be in place after the filter system. But you see, we do have a filter system in place. And if we were using surface water or well water, more than likely this would be a sand media filter. And you see we've got main lines, and then we have some pressure control. So again, we're monitoring the line pressure to make sure that the system isn't over pressurized. We need to put some drains in occasionally, and if we have a controller, you see the solenoid valve where we could shut the water on and off into the zone that we were going into. It would be very easy to put a T in and add additional zones in this system. And you see from the main line, then we go to sublines, and then we have our drip line. So some of the components, we'll just walk through some of these. Again, if we were using municipal water where we were coming off of a hydrant, we could use something like this hose thread backflow preventer or atmospheric vacuum breaker, something to keep anything that we might do to the water on our end from going back into the shared system. On a larger scale, the picture on the right is an RPZ, or a reduced pressure zone backflow preventer. And this particular grower has tapped into the municipal water just on his side of his water meter, and has installed the backflow preventer. And you can see the backflow preventer is just to the left of those two green posts. And then as there's some gray connections, and that's a little bit of a pressure regulator. And then you see the white PVC tied into the blue fertilizer injector. And so his backflow preventer is between the water source and the fertilizer injector. So anything that may potentially get sucked back into the line will not get back past the backflow preventer and into the municipal water source. It is, if you're going to tap into municipal water, it is very much recommended that you contact your water provider and ask them what type of backflow preventer that you would need, and make sure that you are doing that correctly, because if there was an issue in which you potentially contaminated the water source, there could be very, very heavy fines, and this is not something we want to do. This would be an area where we're not wanting to skimp. We want to make sure that we are following municipal guidelines for the area that you're in. As we move further down the components, we think about the different filters. The picture on the left would be an example of screen filters. And again, if we were utilizing On a small scale, a municipal source, this filter system would be all we would need. The picture just kind of shows you the inside of the filter, and there's a replaceable wire mesh screen that can be taken out and cleaned. And you can also see below it there's a valve that we can open and close and flush those screens out as well. And as we look to the photo on the right, this grower is utilizing a pond to irrigate his crop with, and you can see he's got a gas-powered pump that is pulling water out of the pond. And then he has put sand media filters on a trailer, which is a pretty good idea, because now he can move them out to his water source, and he's pumping water from the pond into those filters, and they're going to be filtering out debris, algae, things like that. And from the sand media, from the filters themselves, you see there's a couple of thick lines. One's on the top is a blue lay flat line, and the other one is a large blue stripe line that's pumping water out. Those are his main lines that are going out towards his field. When we think about pressure regulators, again, this is important because too much pressure or force can blow out our drip lines. So we have some that are, if you look at the picture on the left, some of them, they're going to reduce the pressure down to 10 psi or 12 psi. Different size regulators, they have different reductions in them to help regulate the pressure. Or the photo on the right is an adjustable regulator. You can turn the valve on the top and adjust the pressure to where you need it to be. As we think about controllers or timers, we don't necessarily need those in our system, but it is very easy to incorporate them into our system to help automate it. And so we can program these timers, and they can be tied into solenoid valves, as you picture on the right. And so as the water would kick on, based on the programming that we have in the timer, it would open the solenoid valve and allow water to flow into that zone. After the duration was over, it would switch off, and then that solenoid would close. So it's just an automated way to open and close a valve, basically. If we did not have a timer or controller system in that, but we still wanted to zone, we would definitely want to have valves in place where we could manually open and close different zones to allow water to pass through into our drip lines. So we also need a main line. This is the tubing or the hose that we're going to run from our water source, our filter system, to the field, to our drip lines. And so this can be lay flat hose that comes in different diameters, or a lot of folks are using the polyethylene hose. It's probably a good idea to use either the lay flat or this black hose as opposed to the white hose, because even the white hose lets enough light through that if there's any bacteria in the water, that sunlight is enough to make that bacteria multiply in your system, and that can clog up your emitters. But by having either the lay flat or this black tube, then we're eliminating any type of sun exposure and minimizing our bacteria growth in that situation. Also, with the lay flat hose, we when the system is not pressurized, there's not water in that, we can drive over those hoses no problem in the field. So that's something another thing to think about when we're laying out our system is how are we going to be able to access our fields. And by putting in this system that lays on the top of the ground, we would still be able to drive over it if needed. When we are going to be hooking the component that we hook from our main line into our drip line, we have a couple of different options. Tape lock adapters. When you're looking in in catalogs, you'd be looking at, this would be the name that we would look up. These are reusable, leak-proof connectors. Like I said, they go between the main line and the drip tape. The picture on the left shows examples of adapters that are put into flatline as opposed to adapters that have been put into that polyethylene hose, which is a little bit more, it's a more rigid hose. But you can see the adapters on the right also have valves in them, so you could individually open and close a specific drip line. And most of the time, T-tape is going to come in either 5/8 or 7/8. Those are the two most common sizes, but there are some companies that sell different size tape as well. And these adapters have different, what we call barb ends. So in these two pictures, those would be, the barbs are the 2 points that are facing each other in the picture. And those come in different sizes. I believe the one on the right would be a 250 barb, and the one on the left would be a 400. And the larger the barb opening, the more water that is allowed through into the drip tape. So that can help increase our flow as well. I do want to mention, besides drip tape, we can also use this system for point source emitters. And so when we look at these pictures here, we see the main line in the picture on the top left, and the adapter that we would put in the picture on the top right. We would put the orange barb, puncture, put a hole in the main line, put that barb in, and that's actually a pressure compensating emitter. And once we put that in, then the smaller tubing that's in the bottom left can attach to the barb or the black end on that emitter and go from that to the stake, which is in the bottom right hand corner, and then that stake can be placed by a plant. We could do we actually utilize this system in one of our high tunnels at Dixon Springs in our hydroponic system. We're basically using all the same components in drip irrigation, but instead of hooking drip tape into our main line, we're hooking in these point source emitters. And so we'll put those tubes in, connect them to the stake, and then put those in each of our buckets for hydroponic production. So I just want to put that in there, maybe the flexibility of this system for different types of irrigating, not just solely for drip irrigation. Okay, so when we talk about drip tape, it comes in different sizes, thickness, the emitter spacing, and flow rate, all things that we need to look at. And so this table below, so actually the picture on the top right is a piece of clear drip tape. You would never buy clear drip tape. This was just for demonstration purposes to show you what the emitter orifice actually looks like inside the drip tape. And so you can see we have water's going to flow through that tape and go into that channel. We see lots of zigzags, and then eventually it will drip out through this tiny opening or orifice. And so that's just what an emitter, when we talk about emitters, but this is what one actually looks like. And in the chart below, we can see we can have emitter spacing anywhere from 4 inches up to 24 inches, depending on the manufacturer of the tape. And if you see, like in the second column, 8 inches LF stands for low flow, or 8 inches HF stands for high flow. And then it will give you the flow rate in gallons per minute per 100 feet. And so we can see the difference between the flow rate on an 8-inch, let's say T-tape with 8-inch spacing, the difference between low flow versus high flow between those two. and then also it gives you the maximum foot run that you could use to maintain this flow rate. When we're picking up buying our components, we don't want to forget these couplers or splicers. Inevitably, you will get leaks in your drip tape, and you're going to need these. The leaks are very easy to fix. We see, critters like to chew on them. Maybe we get a little carried away with a hoe and make a nick in one. And so we see a leak, and we can basically cut that out and put this coupler or splicer in, and we can very easily fix the leak. We usually walk around with a bucket and scissors and several of these couplers when we're scouting our fields, scouting our rows and looking for any problems. If we see a leak, we can just fix it right away. There are a lot more components out there besides just these. These are just some of the basic ones that we would need to get started. But now let's talk a little bit about water sources and factors to consider. We've talked about municipal water. We want to make sure that we have an adequate volume, and that we are able to regulate the pressure, and that there really needs to be some type of backflow preventer in place. And again, I can't stress enough to check with your local municipality and see what their requirements are. We also have surface water. That can include something like a pond or a lake or even a creek. Some issues that may arise with surface water are, what are the potential contaminants in that body of water? What type of drainage is going into your pond? Are we seeing runoff from row crop fields where we may have herbicides that run off into this pond? Are we surrounded by, maybe we have watershed off of a cattle pasture? Is there any type of bacterial, maybe E. coli that's running into our water source? Also, some of our fungal pathogens for fruit and vegetable crops can be found in surface water sources. So we need to think about what potential disease-causing organisms could be in there. We also need to think about, is it an adequate size to meet the irrigation needs? And also thinking about algae. Algae can be a very big problem in clogging up our system. And then also we could utilize a well system. We need to think about, do we have any sand or sediment problems within our well? What about iron? A lot of times we hear about well water being higher in iron than other sources. So no matter what your water source is, I think it's a really good idea to get your water sampled and have an analysis run on it so that you know what factors you may need to mitigate. You would like to be preventative as opposed to having to correct an issue down the road. If we can sample our water and have it analyzed, we know what things we need to correct before we ever start pumping water through the system. And so when we think about utilizing municipal water, we need to make sure that our meter is sized to supply enough volume for adequate flow rate, or our system won't work properly. So a lot of our residential meters are typically the 3/4 inch, and that's enough water to, everybody can shower, do laundry, no problem. But if we think about how we're going to water out through a field, we may not have enough capacity in our meter to meet our needs. And so, this chart just talks about the potential flow rate of different size meters and what our range could be. And then as we continue to think about flow rate, we need to think about the size of our main line. If we size our meter appropriately, we don't want to then negate the meter size by using a main line that's too small, that won't carry enough water to meet our needs. And so not only do we think about our meter size, but also our main line tubing or size. And so thinking about calculating the flow rate for what we would need, we look at, as an example, we've decided that we are going to grow with a T-tape with an emitter spacing of 12 inches, and we're going to use high flow. And at a high flow 12-inch spacing, from our chart, it tells us that we would need a flow rate of 0.25 gallons per minute per every 100 feet. And let's say in our small setup, we have 20 rows that are 100 feet long. So we would take our gallons per minute times the number of rows, and that would mean for our system, we would need a flow rate of 9 gallons per minute. And so if we look at, if we go back to our flow rate for our meter, and if we had a 3/4 inch meter, our range between 2 and 30 would be adequate to meet the 9 gallon per minute flow rate. So our meter would be fine at 3/4 of an inch. But then we need to look at the size of our header line that we might need, or our main line. And so a 1/2 inch line has a flow rate of 6.8 gallons per minute. And that's not going to be adequate. We're going to need to have a main line that would be at least 3/4 inch size line, because at that point we're able to have a flow rate of 13.6 gallons per minute, which would meet the needs of our system that we calculated at being 9 gallons per minute. And so with surface water, there's just a couple of pictures as examples of if we have a contamination in our pond. This picture on the left is strawberries, that there was a runoff from cornfield with atrazine. Atrazine was in the surface water in the pond. In this particular instance, the grower was using overhead irrigation, but that pond water was still had herbicide contamination, and you can see the injury that it caused in his strawberry field by utilizing that water. And then the picture on the right, just as an example, we want to make sure that the size of our pond is adequate to meet the needs. If we're going to be utilizing irrigation because we're in a drought type situation, is the pond big enough? In a drought situation, are we going to dry it up in a day or two, or can it sustain the draw that we would have on it to irrigate? And also with surface water, algae is a really big concern. And so we want to make sure that we have screens on our inlet hose, the hose that's going from the water to the pump that's sucking the water out of the pond. Make sure we have screens on that. And also we would have a sand media filter in place as well. And we would not want the inlet screen to be on the bottom of the pond. We would like to suspend that on some type of off of the surface somehow, if it's on a floating raft or a piece of styrofoam, something to keep it from being on the bottom of the pond. And so if we think about management, the number one thing with the strip irrigation is daily scouting. We're going to need to be monitoring soil moisture. We're also going to need to be checking the system for any malfunctions, whether we are noticing a leak or a clogged emitter, or maybe we need to flush our filters, check our filters. You should be out monitoring your crops as well, scouting for different pests and looking at their growth. And so, just incorporate your daily scouting to include also your irrigation system. And as we think about monitoring for moisture, most of us, it's very, very common for us to use what we'll call the feel method, where we walk by and stick our hand in the soil and pick some up and rub it in our hands and go, yeah, it feels pretty moist to me, or well, it's a little bit dry, I might need to turn the water on. That's better than just driving by and looking at it out the truck window and going, well, the soil looks a little light, I probably need to put some water on it. So we do use the field method. I think it's helps keep us in tune with our plants and our production system in general. But I think using that in conjunction with some other tools like a tensiometer or electrical resistance-based sensors that actually measure the energy that's needed to pull moisture from the soil. We think of it as like a dummy root, and it helps us put a value on how much water tension there is, and helps us make decisions in when to irrigate or not to irrigate. So in this picture, when we talk about clogged emitters, we look at this picture. This is peppers, you know, in Florida, so we can see that the sand is really, the soil is very sandy. It was in a plasticulture system, and this gives a really good visual of when we have a clogged emitter. And if we hadn't pulled the plastic away and had this cutaway of the soil below, if we were walking through the field and looking, you know, the plant on the far left is darker green. It's a little bit perkier, just looks healthier as compared to the plant immediately to its right. And then, you know, the next two plants are a little bit better. They're still not as great as the plant on the far left. And so if we were walking through the field, we might say, well, I wonder what's going on with this plant. Do I have do I have some type of disease issue? What's going on with the root system? You know, what could be happening here? But if we do this cutaway, we can see that we have a clogged emitter. And so this plant is not getting the water or potentially the nutrients that the other plants are getting. And so this just to me gave a good visual of what's happening in the soil when we have a clogged emitter. So things that can clog our emitters, we can have, they can be physical barriers, be it sand or silt, things that get by if we don't have a filter system in place, or maybe we've let our sand media filter fill up, and now we're starting to see some debris flow into the line. That can cause a problem. There can be biological barriers, thinking about algae or bacteria that we've talked about. But we can also see chemical residues that can clog those emitters, whether it be from calcium or magnesium, iron, maybe even manganese, and fertilizer as well. If we don't have, if the fertilizer wants to precipitate out a little bit through our irrigation, then it can also clog emitters. And so within these systems, it's always a good idea to be able to flush the lines. And so putting some checks in place where maybe the end of our main line, we have a valve that we can open and flush that out. Maybe also the end of our drip tape, we can open that up and flush that out as well. And so it's a good idea every so often to just flush your system to make sure that any particular contaminants can roll out of the system and hopefully not clog the emitters too bad. And as we think about a tensiometer for moisture management, again, this measures soil tension, and this is a really neat tool. It has a ceramic tip on the end and basically a pressure gauge on the top, and we fill that tube with water. And when you get a tensiometer, there'll be a booklet with instructions on how to set it up and install it. And as we put that into the ground, the ceramic tip acts sort of like a root system. And so as the water dries down from our soil, dries up, it's pulling moisture out of the tube. We have put water in the glass tube above the ceramic tip, so it pulls water out of that tube and then increases the amount of pressure on the vacuum that we have inside this this gauge. And then conversely, as more moisture is added back into the soil, either through rainwater from Mother Nature or our irrigation, then that ceramic tip pulls the water back out of the soil and up into the tube and lowers the pressure on the gauge. And so it helps us to keep our moisture and our levels a little bit more even. We would try to not go from super dry to super wet. We want to try to maintain an even moisture amount, and this is a good tool to help us do that. They come in different sizes. The one that we have at Dixon Springs, because we are now doing research just in high tunnels, we have permanent raised beds that are about 6 to 8 inches deep. And so we are just utilizing a 6-inch tensiometer, because our root system is not going to really be going much deeper than that in those raised beds. Out in the field, you know, you could get different lengths of tensiometers of, you know, 12 inches, 18 inches. You can even get up to 24 inches. And so you want to put those where the you want to select the length that's going to put that tip into the main portion of the root zone, so that you can monitor the moisture and not only just water uptake, but maybe also the availability, the nutrient uptake potential that system has based on the moisture in your soil. Threw together some resources, just really quick. This is by no means an exhaustive list. There's a lot of information on drip irrigation out there. I think one of the best suggestions I could give would be, as you think about setting up your system, find a vendor or retailer, irrigation dealer that you can work with, get them on the phone, talk to them, start a relationship with them, because they're really going to be helpful. They're the experts in this business, and they can help you size the different components of your system based on the size of your farm and some of those parameters. And so when you make these phone calls, you know what your soil type is, have an idea of the area that you plan to irrigate and maybe expand to in the future. Be able to tell them what type of crops, so that they can help you decide on drip tape spacing and different things like that. And so here's just a list. There's a irrigation in the Pacific Northwest. This website is shared by Washington State University, Oregon State University, and also the University of Idaho. So you have irrigation specialists from all 3 states that put information onto this website. There's a irrigation supplier from out of Louisiana at Irrigation Mart. They've got some good general guides for additional reading. Also, DripWorks out of California, they've got a pretty good drip planning guide as well. And then for a Midwest supplier, we've got Indiana Irrigation. They're located just outside of Indianapolis, I believe. But again, not promoting any particular vendor or supplier, just putting these resources out there as an example of places you can go to look around for information and components for a system. And with that, come to the end. I want to thank you for spending your lunch hour with me. And I don't know if we have any questions, but I will see what we've got, what we can do in the next couple of minutes before the session ends.
Great, thanks, Bronwyn. Yeah, we have a few questions, Ann, and I've got a couple of questions myself. So we'll start with the questions that are in the chat box. The first one I attempted to answer, but maybe we could get your perspective on it. It wasn't necessarily pertaining to drip systems, but the question was related to valve solenoids that can operate at less than 10 PSI. They're looking for draining some greenhouse water tables, and I pointed them. There are some. There's a brand called Bacara. They have an AC valve that operates at like 4.3 PSI, but are you familiar with any valve solenoids that operate at less than 4.3 PSI?
No, not off the top of my head. I think, again, that's where you go start looking around at some of the different suppliers. And if you find some suppliers that are maybe geared more specifically to greenhouse systems versus in-field irrigation systems, they may have products that will meet that lower PSI requirement.
So a question came up about the color of the hose. I know you talked a little bit about not wanting it to be clear. in terms of main line or sub main lines. But the question was more focused around the color of the hose in greenhouse versus outdoor. I said it shouldn't matter, but I thought I would just go ahead and ask.
Yeah, I think, no, I don't think that would matter. I'm assuming there might be thinking about if with the dark hose that it may heat the water up more.
Right.
I don't think that's going to make much of a difference, especially, if they're looking at a point source emitter system, if it's a hydroponic type situation, the water going into the media in those pots, that media is going to kind of help cool it down if it was to get hot. But I think you turn that system on and it's going to run through, and you'll be running cool water pretty quickly. So
right. So about gravity fed systems using rainwater, someone had the question in terms of how could you use drip for that. I know that there are gravity fed drip possibilities and even pump possibilities from stored rainwater systems. Any comment about that?
And I'm not going to be able to remember the exact numbers, but there were in looking up information for this presentation, there were definitely some sources of information out there for gravity fed systems. And basically you're going to want to your holding tank, you're going to want to elevate that. And again, this is where I'm not going to remember, like, there were some of the diagrams that at a specific height, you could feed this much line, linear feet of line. And so I don't know how high that holding tank needed to be. I don't think it was something like 10 or 15 feet. I think it was, in the 5 to 6 foot range approximately. Like I said, there was a lot of information out there that would give some more specific calculations and heights for that. But I think it's, especially, we're in a low pressure system anyway, and so gravity fed can definitely work in drip irrigation.
Right, you just need to size your components appropriately, and there could be some height issue, like you mentioned.
Yes.
The higher you have it, just like a water tower in a municipality,
Yes.
the higher, the more pressure you have. So
yeah, or if you want to put a pump system in that, a lot of times, if we're looking at a gravity system, maybe we're not somewhere where we are readily accessible to to electric. If we wanted to run an electric pump, or put a really small gas pump on that, that would work as well. But
same person had the question in terms of components being compatible with hydrogen peroxide. I think the answer to that is yes. I know that I would definitely read the label, make sure it's labeled for injection in irrigation systems. But I know there's definitely peroxyacetic acid is approved, and that has some level of hydrogen peroxide. And any comments about that?
Yeah, I think your suggestion is right, Zach, to make sure you read the label and see about that. Most of the line, we've talked about if we need to have a chemigation station to help control. Sometimes we can put a chemigation station in as we're helping to control algae, and so maybe we need to inject a little bit of chlorine into the system. And so there's definitely the components can definitely withstand a little bit of those different chemicals, but again, I think reading the label would be the best recommendation.
Okay. A couple more questions streaming in here. I guess as a follow-up, solar pump with the rainwater catchment system. As a follow-up to that, I guess I would just make sure that the pressure requirements and flow requirements are being met by that solar pump.
Yeah, I don't think there would be any problem with solar. You just want to make sure that you can get the right pressure. Yeah.
Can a drip tape off a main line be replaced with a tape or line with point source emitters as plant configurations change from season to season, as an example, in different crop rotation?
Yes, and if you wanted to reuse your main line, they do sell things, and they actually call them goof plugs. So if you have made a hole in your with the punch in your main line, and then you want to reuse that main line the next year, and your drip tape isn't in the same place or same configuration, you can put those goof plugs in. Clog, basically stops that hole up, and then you can put a different hole in, and they make a fitting that you can put in to run point source emitters off of that. So yeah, it's very easy to reconfigure.
Like you were saying, these are such configurable plug and play systems. As long as the pressure and flow requirements are met, then you can
Yes.
pretty much do whatever you want, right? I mean, as long as you.
Yes. When you start going to some of these irrigation supply websites and just start looking at all of the different components and fittings, you're just like, wow, I can make this system do just about anything I want. Again, as long as it's going to meet the flow rate and pressure.
Yeah, and just as a reminder, with drip tape, it's usually flow rate per 100 feet, and emitters and overhead sprinklers are usually flow per individual meter. So you just have to add everything up correctly.
Yep.
Let's see here. I think no more questions from the audience. I had a couple questions and maybe one comment. One related to, you had the slide about pressure or friction and pressure loss, and it was related to, I think, a water velocity of 10 feet per second. Any comments about, we talk a lot about pressure and flow with these systems, but there isn't a lot of discussion about the velocity of the water. I've seen suggestions that if it's above 5 feet per second, that you could have issues depending on the size of your pipe. Any comments about that? Or I know there's charts you can look at in terms of the size of your pipe and the I think the pressure, and it gives you the velocity of the water.
Yeah, I think again, talking with your irrigation supplier, they're going to be the experts in this field, and they'll be able to answer those questions pretty well. But I think as we think about the bigger diameter of pipe, the less friction that we will see. And if we think about, there is laminar flow and there's turbulent flow within a pipe. And the smoother that the inside of a pipe or a hose is, the less turbulent flow that pushes against the laminar flow. And so the better the laminar flow, the less friction. And so a garden hose, we think it appears to be pretty smooth on the inside, but actually it's got lots of rough little spots and cracks or crevices in there, and it causes a lot of turbulent flow. And so that the type of pipe that we choose and the size of the pipe, I think, can have a direct correlation on that velocity.
Interesting. Yeah, for our new demonstration site, because we're tapping into municipal water, but we're having to take the municipal water from a building and bringing it out to where we're distributing it. So we have to make sure, and I didn't comment on this, but I think it's important to remember that if you have a system where the water in your piping is under constant pressure, that you have to size the pipe appropriately, and that pipe has to be rated for constant pressure. Like in the case of if you're putting a new line out from your well pump to your greenhouse, that piping that water will always be in there under constant pressure, and it has to be rated for that. So it was kind of a tied in with that too, in terms of.
Yeah, and I think, in our field situations, a lot of times we may see growers that will run PVC pipe underground from their pump up to, the front of their field, where they can then tie in with header line that, is easy to tap into as far as hooking the drip line into.
Right. Okay.
Yeah.
Okay, good. Well, I think that is all the questions we have. Someone did comment about getting a copy of the slides, and we can probably get a protected PDF from Bronwyn and send that out if she'd be willing to send that out to me, and I can get that out to everyone. But with that, I'll go ahead and thank Bronwyn for joining us today and giving us some knowledge related to drip irrigation. And thank everyone for joining us today. Hope you got a little bit out of this, hopefully enough in time to design your drip irrigation system for the upcoming growing season. Look for an email from us with the archive link for the webinar as a short evaluation. The QR code is being displayed right now. You could do the evaluation in real time if you want. But we look forward to your feedback to really help shape our future webinars. And with that, have a great rest of your day. And if we don't see you for the last webinar last week, have a great 2020 growing season.